Hello everyone, welcome back. In this video, let us discuss about minimum cost spanning tree. In the previous video, we have seen how do we construct a spanning tree from a given graph. There are few conditions that has to be followed when you're constructing a spanning tree. So we saw that a spanning tree is nothing but from a graph when you're generating it, it should have same number of vertices as given in the graph, as well as there should not be any vertex that is left out. All the vertices should be connected, and the number of edges should be one number of vertices minus one, that is one less than the number of vertices, and which should not have any cycles in the spanning tree. There should be no cycles. So what is minimum cost spanning tree? A minimum cost spanning tree is a spanning tree of an undirected weighted graph with a minimum possible sum of edge weights. So it is a spanning tree that connects all the vertices of the graph with a minimal total cost. So let us see an example. We have an example graph here. This is an input graph which has 7 vertices, and we can see that all the vertices are connected with edge, and each edge has associated weights. And we could also see that there are cycles in the graph. So when you are forming a spanning tree, the spanning tree should not have cycles. There should be equal number of vertices as in the given graph in the spanning tree also, and none of the vertices should be left out, and it should form a minimal cost. So here we have a minimal cost spanning tree which satisfies all the condition of a spanning tree. The number of vertices are as same as that of the graph. 7 vertex here, 7 vertex in the spanning tree, and there is no cycle in the spanning tree. There is no vertex that is left out. All vertex are connected. So it is a spanning tree. Now how do we say whether it is a minimal spanning tree or not? We should add the cost of the edges and see whether it is forming a minimal spanning tree. So let us consider another example which will form a spanning tree. So let us discard this edge as well as let us discard this edge. Let us generate an edge between 5 and 7 which is there in the given graph, which has weight 24, and there is also an edge between 7 and 4 with weight 18. So we have a weight here that is 18 and a weight here that is 24 associated with this particular edge. Okay, so in case these two edges are not there, 14 and 22, but instead we have these two edges, it is still a spanning tree because all the vertex are there as the vertex are given in the graph, and all the vertex are connected. There is no left out vertex. It's all connected, and there is no cycle, because don't consider this as a cycle because this edge we are removing. In case we delete this edge and we delete this edge also, and instead we add these two edges, there is no cycle in the graph, as well as all the vertex are connected, right? Now, but what will be the total cost? 24 plus 18 will form 42, whereas 22 and 14 was giving a total cost of 36 only. So 36 is smaller than 42. So if we add these two edges instead of an edge between 5 7 and between 7 and 4, which is costing a total cost of 42, and if you are adding an edge between 2 and 7 and 5 and 4, it is just costing a total weight of 36. So we have to choose edges in such a way that those edges should give me a minimal total cost. So such spanning tree, we call it as a minimal cost spanning tree. So let us remove this. Yeah. So this is a minimal cost spanning tree which is forming the minimum cost between the edges, or as an overall spanning tree. So what are the application of this minimal cost spanning tree? It is used in network design, transportation planning, resource allocation, etc. Now, given a graph, how do we construct a minimum cost spanning tree? There are two algorithms for this, called Prim's algorithm and Kruskal's algorithm, which will be used to construct a minimal cost spanning tree from a given graph. We will discuss about Prim's algorithm and Kruskal's algorithm in the forthcoming sessions, and that's all for this session. So in this session, we have seen what is a minimal cost spanning tree and what are the methods to construct a minimal cost spanning tree from a given graph. Thank you so much for listening.